All right, welcome back to Differential Equations, and this is going to close out. This is the first part of Laplace Transforms for us. I got one more topic to talk about, and I could probably do it for 2 videos. Sorry. So we're probably going to be, we have one more topic to talk about, and that is called the unit step function. Okay, it's also called the Heaviside function. I should capitalize it because it's after a person's name, named Heaviside. Okay, and you've seen unit step function before. Okay, all we're going to do is, like, the function is 0, okay, up until a certain point, and then actually I'll put a open dot here, and then it'll pop up to 1. Okay, and you can multiply this by, like 7 if you wanted to. Okay, and it'll pop up there, and then it's 1 from then on. Okay, so unit step function f of t is equal to, and it's 0 when t is less than or equal to a. Nope, just less than a. And then 1 when t is greater than or equal to a. So once we hit a, pops up to 1, goes on forever. 0 until that point. All right. If we go ahead and multiply by, oh, by the way, the notation for this is u of t minus a, and this means, right, at a, so f of t, f of a, f of t minus a is going to be at the a point. That's when it's going to pop up. Okay, so this should really be f of t minus a. Right. If we multiply it by something, like, say, for example, I've got unit step function t minus a, and I put like a 3 here. Well, then it just decreases it by 3, right? It just changes it. So instead, I have the same graph. So we're up here until, let's put a 1. Let's put something in here. Let's put a 4. So 1, 2, 3, 4. Okay. And then 1, 2, 3. Okay. So it's 0 up until this point. And then it's there. And then on forever forward. Okay. It's a little bit more interesting when you do something like a u of, say, t minus 2, and then do like maybe t minus 2 squared. Okay, so again, we're 0 up until this point, right? And then at 2, well, technically the unit step function is doing this, right? But it's just multiplying it by this parabola piece here. Okay, so notice we're not going to have anything over on this side, right? If you put a -1 in here, like, well, this is 0, so 0 times whatever this is still going to be 0. So what's going to happen, right, is that this part here, this is the unit step function, is going to multiply by this, and 1 times this part down here is just this part down here. So that's how we can turn functions on and turn them off. Okay, so if I wanted to say, do something like, I hate to do sines or cosines just yet, but like, say, for example, I wanted a function that looked like sine t, and then at, say, pi over 2, so 0 between t and pi over, or was it 2 pi? Okay, sorry, I meant 2 pi when I said pi over 2. And then say I wanted to get rid of it, right? I only wanted one cycle of the sine and then nothing else ever again. So we'd have a minus u of t minus 2 pi, right, times sine of t minus 2 pi. Technically, you don't need this because your sine is a repeating function, right? But just to keep things going to look like something you're going to do, I want to keep the arguments the same. Okay, it's a lot easier for Laplace transforms when these arguments are the same. If they're not the same, you got to force the issue. Okay, we'll show you how to do that in a minute. Okay, so what's going to happen here is right, we get the sine function, right, for one cycle, and then what we're going to do is we'd still have a sine function, but we're subtracting off, right? Because this doesn't turn on until pi over 2. But when it comes here, we're gonna have a sine function here that's the opposite, and these two waves are going to cancel out. So what's going to happen is we're just going to see the graph of this, and that's it. Okay. So what does this have to do with Laplace transform? Like, well, for electrical engineers here, you guys have a lot of times when switches turn on at certain times, and there's circuits that you have to take differential, that are expressed as a differential equation, and you're going to have to solve this. Okay. And the way you're going to do that is you're going to use Laplace transform to do it. So one of the questions you might have is like, well, what's the Laplace transform of the unit step function, right? What's this? And then let's go with a t minus a here. Okay, so a could be any point you want. Okay, it's usually positive. Okay, because Laplace transforms, we usually talk about the integral, right, from 0 to infinity. So we don't really worry about what happens before 0. Okay, and it's still the same definition. Here's e to the negative st, right? And then here's my unit step function of t minus a. Now, until a, right, this function, this is 0, okay? Because the function, the unit step function says, if t is less than a, right, then u is equal to 0. The unit step function is 0. All right. So couldn't I replace like this integral as from 0 to a of e to the negative st u of t minus a plus integral of 0 to infinity, or sorry, a from 0 to infinity e to the negative st u of negative t. Okay. Now, from 0 to a, this part here, right, this function here, this is 0. So the integral is 0. Okay. So we're just going to put a 0 in there. Plus, and then what we're going to do here, right, this is just going to be integral from a to infinity. But once we hit a, right, the unit step function is 1. Okay, so all we have to do is integrate from 0 to infinity, or a to infinity rather, a to infinity, e to the negative st dt. And that is our Laplace transform of the unit step function. Okay, let's go ahead and evaluate this. Right? So this is going to be 1 over negative s, right? E to the negative st. We're going to go from a to infinity, right? So it's going to be 1 over negative s. Okay, and then we have e to the negative s. I'm going to use a capital T. That's my limit as t goes off to infinity bit. Okay, minus e to the minus s a, right? So this is 1 over negative s, 0, right? Because this t goes off to infinity. This term here turns into a 0, minus e to the negative sa, right? And then all we have here is e to the negative sa over s, right? There's a negative and there's cancel. What was the Laplace transform of a constant? Right? This is the Laplace transform of a constant. It's just a. Wasn't this just 1 over s, right? Or a times 1 over s. And then this part here is e to the negative sa over s. Okay. If there was a constant, if we multiplied the unit step function by 3 or something, we would have put that outside the integral, and we'd still have a times, right? So if we change the height of the unit, instead of the unit step function, we had like the 3 function, we would have so if I want to do a Laplace transform of 3 u minus 2, okay? What that's going to be is 3 times e to the negative s times 2, right, divided by s. So it's going to be 3 e to the negative 2s over s. Okay, so it's the same function, right? This is 3 over s. This is the same kind of thing. If I just took the Laplace transform of 3, we'd have a 3 over s. What's different? is we have this e to the negative as term to signify that we had a step function, right? And that's all you have to remember for this, right? So if you have the Laplace transform of u of t minus a, okay, f of t minus a, that's going to be e to the negative sa over s times f of s. All right. Maybe we should do a function. Okay, just to have an example for it. All right. So let's pick an easy one. Okay. That we can integrate. How about something like how about we do this? How about we do a Laplace transform, right? U t minus 3. And let's just pick a polynomial here. Let's pick a t minus 3 squared. Okay. Again, it's really important that these arguments are the same. Okay, like I said, if they're not, we're going to force the issue. And I'll show you how to do that one in just a minute. Okay, but this is what we're going to have for a second here. Okay, second here, pause. Okay, so again, just like the other pieces, once we get the idea of doing this by hand once, you're going to be consulting a table. Okay, I don't want you to have to go through this every time we're going to do it. That's just not how this is done. Okay, so Laplace transform. Okay, that's going to be integral from 0 to infinity, right? E to the negative st. And here we have unit step function, t minus 3, okay, times t minus 3 squared dt. All right. So let's see how this is going to work. What I want to do is I want to introduce a new variable. Okay. So we're going to say let's something I can write. Right. Let w equal t minus 3 or something. Okay. So w plus 3 will be t. dt is equal to dw, right? So every time we make a substitution in calculus, we take its derivative, right? And I'm just going to start replacing t's with w's, right? So this is going to be 0 to infinity. Actually, we have one more thing to fix, right? We have one more thing to fix. So the limit, right? So when t equals 0, w is equal to 3. All right. And when, or as t goes off to infinity, w, right, goes off to infinity. Or w goes off to infinity. All right. So make that an actual w instead of a t. So as t goes off to infinity, w also goes off to infinity. And then one more little, I mean, this one's obvious, right? When t equals 3, w equals 0. Okay. All right. So what I'm going to do here, okay, is I'm going to keep it in t space for just a moment longer. So we're going to have integral from 0 to 3, okay, e to the negative st unit of t minus 3. And then we have t minus 3 squared dt plus integral of 3 to infinity. Okay. And once we're at 3, right, this is turned on. This is now 1. Okay. So I'm just going to write this down. This is u of t minus 3, t minus 3 squared. Okay. So until we get to 3, right, from 0 to 3, this function here, this is 0. Okay, so this whole part here, this is just going to be 0. All right. So we're just going to have the 0 plus, right? And once we get to 3, now we're going to have our t to 0 to infinity e to the negative st this is here, right? Once we get to 3, this unit step function, this is now 1, right? And we just have t minus 3 squared dt. Here's my change of variable. Okay, so now I'm going to sub w for t. Okay, so my integral, right, going from 3, w was 0, still going to infinity. We have e to the negative s. This is w plus 3, isn't it? W plus 3. And then t minus 3, that's just w. W squared dw. Okay, so this is e to the negative 3s, that's this part, and which is a constant, right? Because we're integrating with respect to w, not with s. 0 to infinity, right? E to the negative SW, W squared, dW. Isn't this the Laplace transform, right? This is the definition of Laplace transform. So this is the Laplace transform f of s, right? Where f is t squared, W squared, okay? So we're just going to say this is equal to negative 3s, and then W squared is going to be 2 factorial over s to the 2 plus 1, okay? So this is what happens, is we just get 2e to the negative 3s over s cubed. So this 2 over s cubed, this is the Laplace transform of the parabola function. And this e to the negative 3s, that tells you when does this thing turn on. Okay. And when we go backwards, we're going to be looking for these. Okay, we're going to know that, hey, that's a unit step function. We're going to be able to look at the table and figure that out. Okay. All right, what happens? What if I wanted to do this? What if I wanted, I said f of t is equal to the unit step function t minus 3, okay? But I'm just going to say, like, I want t squared, okay? It turns on at 3, but it's going to turn on 1, 2, 3. It's going to turn on 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's going to turn on up here at 9 and keep going. Right? That's what this would look like. Okay, so it's 0 up until this point, and then it turns on over here. Okay. Here's what happened beforehand. Okay, pretend those match up and they look straight. All right, so it's really helpful if Laplace transform wise, if the arguments match. So I'm going to write 0 in a way that's a little bit weird. Okay, so we're going to say this is u t minus 3. I'm going to say this is t minus 3 plus 3 squared. And I'm going to group these two together, and we're just going to square this out. Okay, so this is f of t equals u t minus 3, right? But this is going to be t minus 3 squared, right? We're going to have 2 of those, so it's going to be 6 t minus 3s plus 9, all right? And then we're going to have to take the Laplace transform. When we do this, we're going to have to distribute. Okay, so that's u t minus 3, t minus 3 squared, and we know what that is because we just did it. Okay, plus u t minus 3. We have a 6 here, and then we have a t minus 3. And now, since these match, it's going to be an easy Laplace transform. Okay, and then we just have 9, right, to u t minus 3. 9 u t minus 3. Right, and that's how you adjust this. So what you really want, right, is, because we showed up here, it was a real easy integral to take if the arguments matched. If they don't match, we got a mess to deal with. Okay, so you really want them to match in order to use the table and make things like nice and easy for yourselves. And this is how you get them to match. You just add 0, okay? We just subtract it, and then, or we add it and subtract it, and then we're good to go. And again, I'm going to pull an engineering teacher trick and say we're not really, when t is less than 0, we're not interested. Okay, so this is usually time. So when time is less than 0, we just don't consider the situations when time is negatives. Okay, if you want to start earlier, then redefine what your t is so it starts earlier. Don't try to deal with negative times. And then we just take the Laplace transform here, right? So if I want to take the Laplace transform of f of t here, that's this thing. Okay, we have e to the negative 3s, right? And then we'd have the Laplace transform of the parabola function, and we know that that's 2 over s cubed, okay, plus 6, right? And then now this is just t minus 3, so just the linear function. So this is 6 e to the negative 3s. And what was the linear function? The linear function was 1 over s squared. Okay, plus 9 e to the negative 3s. Okay, showing us that we started late. Okay, and then we just have a constant, just 1. So 9 over s. And it's e to the negative 3s. That's the same thing in every case. I'm not really sure if you really want to do this or not. I think you probably want to factor that out. So you can group all the parts that started at 3 together. Okay. And just leave it like that. Okay. Now that when you have to do the inverse Laplace transform, you'll have a spot here like, oh, wait, this is my unit step function. So I'm going to have a ut minus 3 here. And then you can go ahead and figure out this part. Okay, this should be, oops, over s. Okay, so that's how we do it with unit step function. All right, and there's a couple of problems in your homework that do that, and I will do those actually right away. So give me a moment, I'm going to run down. All right, so at the risk of me making this a little bit longer, okay, I think I would rather just finish doing our examples here rather than try to start a new problem. Actually, well, it's just 3. They're small. So what we have to do is we have to find the Laplace transform, right, of t minus 1, okay, u to t minus 1. Isn't this convenient? Came out of a textbook, you know it, because the arguments are the same, okay? So all we're going to do is we're going to say this is e to the negative s, right, to the negative s. There's 1 here, right? And then this is just going to be the Laplace transform for t. Okay, so this is just going to be 1 over s squared. That's it. Make sure I'm resumed. Okay. Laplace transform, right, of inverse Laplace transform of e to the negative 6s, okay, over s to the 3. All right. So here we go. I just want you to take a look at this. We're down here. Okay, we're down here at this point. See, Heaviside function, unit step function, right? So it's a slightly different notation, but it's pretty much the same idea here. Instead of the t minus c, it's u of c, and then t here. Okay, that's how they do it. Okay. But all we do is we just say, oh, look, it's e to the negative 6s. That's my unit step function, and then f of s. Okay. So since we have our arguments are going to be the same. Okay. T minus 1. We can go ahead and use our table. Okay. Entry number 27. Okay, this is 27. Okay, so this is going to be unit step function, u of t minus 6. Let's go ahead and make that a parenthesis. Okay, unit t minus 6. And then we pretty much have to figure out, like, what's the Laplace transform of 1 minus s cubed? or 1 over s cubed. Well, this is the parabola function, isn't it? We need a 2 and a 2 here. Okay, so we're going to say this is unit step function t minus 6, so 1/2, and this is t minus 6 squared. Remember, the arguments have to be the same. And then the third one here, this is going to be a little bit more interesting because it's e to the negative s, so it's a 1, right? And then we have s plus 1 here, okay? Now, in this case, we don't have 1 with a product on the denominators. So it's time for everybody's favorite part, and that's the partial fractions, okay? This one's not so bad, okay? We're just going to say 1. I'm really moving this e to the, I'm really just kind of factoring this out for a moment because I don't really want to deal with partial fractions with e's in them. Okay, I think that's pretty fair. So we're going to have a s plus 1 plus b s is equal to 1. So we have a plus b is equal to 0. Right, that's my part there. And then we have a equals 1. Well, if a equals 1, right, that's my constant term, then a plus b, I think b has got to be negative 1. Okay. So this is going to be Laplace transform, inverse Laplace transform, e to the negative s, and what do we have? We have times 1 over s. That's a constant, isn't it? Okay. And then plus 1 over s plus 1. Okay. So recognizing the 1 over s part, that's a constant. So that's just going to be a unit step function of t minus 1. That's 1, right? So don't these match? In this case, they don't have to because we know this is a constant. Okay, so what is f of like t minus a when f of t is 7? It's still 7. Okay, the t doesn't actually, the argument for t doesn't, changing this argument here is not going to change this function. It's constant. Okay, and then plus, and then I've got again this unit step function t minus 1, right? And this is just going to be e, right, to the negative st, or negative t minus 1. Okay, because it's got to be right negative. Okay, so we could, I guess, break this up a little bit and say this is t plus unit step function of t minus 1, and it's going to be e, and we have 1 minus t. And that is the inverse Laplace transform of that one. Okay, I'm going to go ahead and stop us here. And see, I told you there's only 3. And then we'll maybe wrap this up Laplace transform in like the next video, and that'll be that. Okay, so good luck with the homework on this. Okay, I know it looks confusing. They're really not as bad as they're going to have it seem. The only tough part is making these arguments line up. And to be fair, almost everybody has a problem with this the first time they do it. So if you're struggling a little bit with this, just realize that you have the company of everybody who's ever taken this class before to commiserate with. All right? All right. So good luck. Let's go ahead and do that, and I'll wrap up.